You have probably asked a developer or a systems engineer this question before. How much RAM does this program use? It seems like a simple query. It asks for a number. But the answer is almost never a single number. In fact, asking that question is like asking how heavy a suitcase is without knowing if it is empty or full, or asking how much water is in a pipe without knowing if the tap is running. The reality of computer memory is far more complex than a static measurement. Today on Master of Machines, we are going to deconstruct the myth of static memory usage. We will explore why the answer depends on the definition you use, the moment you measure, and the hardware underneath it all. Here is the thing. When you look at a task manager or a monitoring dashboard, you see numbers. But those numbers represent different layers of reality. The most common confusion comes from the difference between virtual set size and resident set size. Think of virtual set size as the total amount of space a program claims it might need. It is the size of the warehouse the program has rented. It includes every library, every file, and every potential data structure the program could ever access. Now think of resident set size as the actual bricks currently sitting on the floor of that warehouse. This is the physical memory currently loaded in the random access memory chips. A program might rent a massive warehouse, but only have a few boxes on the floor at any given time. If you measure the warehouse size, you get a huge number. If you measure the bricks, you get a small number. Both are technically correct, but they tell you completely different stories about performance. Now consider how the operating system interacts with this memory. Modern operating systems are designed to be helpful. They want to make your computer feel fast. If your program is idle and not using all the available random access memory, the operating system will use that empty space to cache files and disk data. This means the memory is technically being used by the program in the sense that it is occupied, but it is not being used by the program logic. It is being used by the system to speed up future requests. If you measure memory usage while the system is idle, you will see high numbers. If you killed a process, those numbers drop instantly. This behavior is often mistaken for a memory leak or excessive usage, when in reality it is just the operating system doing its job to improve performance. The complexity deepens when you move from compiled languages like C or C++ to managed runtimes like Java or .NET. These environments utilize aggressive memory management strategies. They pre-allocate memory to avoid the overhead of asking for more memory while the program is running. This means the application reserves a large chunk of the warehouse floor immediately upon startup. Even if the program is doing nothing, the memory is reserved. Furthermore, these runtimes use a process called garbage collection. This is an automated system that cleans up unused data. Sometimes, during a garbage collection pause, the program stops completely to rearrange its memory layout. During these pauses, the resident set size might spike temporarily as the system compacts the data. If you take a snapshot during this pause, you might think the program is using more memory than it actually needs for its core function. We must also talk about the hardware limitations. There is a concept known as the memory wall. This refers to the gap between how fast the central processing unit can compute and how fast it can fetch data from the dynamic random access memory. As processors get faster, the speed of data transfer does not keep up. In the context of large language models and artificial intelligence, this is a critical bottleneck. Large batch inference often remains memory-bound. This means the performance plateaus not because the processor is too slow, but because the data transfer speeds are maxed out. The processor is waiting for data. In this scenario, optimizing memory usage is not just about saving space. It is about ensuring the data is moved efficiently enough to keep the compute units busy. This dynamic behavior creates instability that standard correctness tests fail to detect. Code generated by artificial intelligence can be functionally correct. It runs without errors. It produces the right output. Yet, it can exhibit drastically different runtime memory behaviors compared to human-written code. One version might allocate memory in a way that causes frequent fragmentation. Another might trigger the garbage collector too often. Both are correct in terms of logic, but one will consume significantly more physical memory over time. This divergence means that a simple test for correctness is insufficient for predicting real-world performance. You could have two programs that do the exact same thing, but one will run out of memory while the other runs smoothly. So, what determines the answer to the question? It is the context of the query. If you are debugging a bottleneck, you care about the resident set size and the actual physical usage. If you are planning capacity for a server, you care about the virtual set size to ensure the process does not crash due to address space limits. If you are optimizing for energy efficiency, you care about how often the system has to swap data to the disk. There is no single number that captures the full complexity of virtual memory, physical RAM, and cache hierarchies simultaneously. The lack of a single answer stems from the interplay between hardware limitations, algorithmic efficiency, and the specific context of execution. Ultimately, understanding memory usage requires looking beyond the dashboard. You have to understand the life cycle of the application. You have to understand the operating system caching strategies. You have to understand the hardware bandwidth constraints. When you hear a metric, ask what it represents. Is it the potential space or the actual usage? Is it the program or the system? Only by asking these questions can you move past the myth of static memory usage. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.